action. Boom. Hello and welcome back to Calculus 1, section 2.3, techniques for computing limits. So the last time I said that you can compute every limit under the sun by working out the chart. You can always default to that. If you can't figure out any other way to take the limit, chart, and you don't know how to graph the function, then the chart will be there to solve the problem and solve the problem correctly every time. However, chart tends to be really annoying and long to calculate all the values, look at the trend, and all of that kind of stuff. So we are going to try and learn as many as possible of these algebraic techniques so that we can solve limits faster. So the first idea is going to be to just plug in the value. Now, the most important thing about this is to understand that it doesn't work all the time. So if you get 0 in denominator or anything weird starts happening, well, yeah, it's not going to work. So, and you can't claim does not exist, because limit might exist. It's just that you're computing it the wrong way. This is the fastest and the most dangerous way to compute limits. If you remember the 4 graphs from last time, only one of those graphs, 1 out of 4, right, had the situation where the function value and the limit value were the same value, right? And other 3 did not have that. So the chances are, most of the time, that this will not be applicable. When this is applicable, it's applicable when you plug in the value, you get a number, and you're done, right? So let's say you have limit x goes to 3 for x squared minus 5, right? This is okay, right? You can use it in this case. So 3 squared minus 5 is 9 minus 5. The answer is 4, and you walk away. So when you have a polynomial of any degree or any kind, you can always use just plug in the value and you are done. You can use it maybe on the, exponential function will also work, right? So let's say you have e to the x minus 1. Well, now you have e squared minus 1, and you can compute the decimals if you are interested in decimals, but that's the answer. Now, if you have limit of 3 over x plus 1, and your limit x goes to negative 1, cannot use it here. Cannot use the method. Because the method will give you 3 over 0. And 3 over 0 can be a very interesting thing for calculus. It can mean undefined. In this case, it actually does. But for certain functions, 3 over 0 could be actually a value of some kind. So we have to be very careful about that. You cannot claim does not exist because you got 0 in denominator. I will give you a quick example of that, and then so limit x goes to 0 of 3 over x squared. The answer is positive infinity for that one. We are going to cover this tomorrow. But as you can see, the answer is not does not exist. The answer is positive infinity. So you did have 3 over 0, and you did not claim. So you cannot claim does not exist if you have 0 in denominator. You actually have to compute. And we will see more of examples of this sort today in this particular lecture. So the first method to compute, and the easiest method to compute limits, is obviously to just plug in the value, and if the value works out to be a finite number like these, you are done. You just walk away. But if you get 3 over 0, if some weird stuff starts happening, then you have to use something else. Now, there are many cases where you have to use something else. For instance, this is the one that you actually have to memorize for now, all the way into chapter 4. 4.7 will tell you how to compute this limit. Now, if you're looking at this limit, right, you say, oh, this is 0 over 0. What do you get when you divide 0 by 0? Well, if you divide 0 by any number other than 0, you should get 0. And when you divide any number by 0, you should get undefined. So which one is it? All right? So 1 tells you that the answer should be 0. 0 divided by any non-zero number should be 0. And over here, any number divided by 0 is undefined. So now you have like 2 answers that are competing for the spotlight. But the answer for this is neither of them. The answer is 1. So you will be asked to memorize this limit in chapter 3, and then the way to compute this limit will be revealed in chapter 4. So still in Calc 1. But you have to understand that plugging in values doesn't work all the time. And in many cases, you will not be able to predict. Does not exist. Because out of 3 examples that I gave you, which all had 0 in denominator in one way or another, right? One was does not exist, one was positive infinity, and one was 1. So please immediately erase from your head if you have it in your head for whatever reason, that plugging in numbers with 0 in denominator is going to give you undefined, because clearly in some cases will not. We are going to move on to other situations. So technique number 1 is plug-in. Now let's see what other witchcraft we have available. Algebra. So certain limits you will be able to work out by working out algebra. For instance, limit of x squared minus 16 over x minus 4 as x goes to 4. What happens as you plug in 4? You get 0 over 0, and then you want to say undefined so badly, but you are not saying it because you know I'll spray you. Just fix this. I'm not a bad cat, right? So you are not allowed to claim that. Let's solve this problem. Don't we know something from algebra that we can apply in the numerator? What can we do? Factor it, thank you. X minus 4x plus 4 divided by x minus 4. Now these guys cancel. And what's the limit? What's the limit? Well, and x goes to 4, so 8. So using these factoring witchcraft, we canceled the denominator, which was bothering us, and we got 8. Who would say that 0 over 0 over there went to 8? You see that? So you must be ready to use algebra to factor, right? If you can factor, you factor. If the stuff cancels, yay. In some cases, it will not cancel. Well, you try something else, and when you run out of options, yeah, chart. When you run out of the options, it's going to be chart. Now, what I want to do is I want to encourage chart on this example, because you might not believe me that the answer is 8, right? So let's do the chart real quick. So we are interested at what's happening at 4. So we need to have 3.9, 3.99, and 3.999 to the left. 4.1 all the way to the right, 4.01 and 4.001. Now, you plug these values into your calculator and solve. Oh, my calculator is in the wrong mode. Give me a second. There we go. X squared minus 16. X squared minus 16 divided by x minus 4. Okay. All right, so what are the values? 3.9. I have 7.9. 3.99 gives me 7.99. You already see that my answer 8 is correct, but you know, let's just enjoy this for a moment. 7.999. Okay, let's go with 4.001. .001. No coffee. Next one is 8.01. And the last one is 8.1. Yeah, it's 8. So I used this function here to compute on these x values, got the y values from the bottom. Let's go the red approach goes towards 8. Blue approach goes towards 8. Well, if it walks like a duck and quacks like a duck, it's a duck. Exactly. There's the duck right there, 8. So, clearly it was much faster to factor and cancel than to do the whole thing of the chart. But you see that the chart does give you 8. So what happens on the exam when you see 0 over 0? Do you put undefined? Well, the answer is hell no, you don't, right? Because most likely your answer is going to be 8 or something like that, right? So you have to be very careful with these calculations. What else is there with algebra? Well, square roots. Square roots are cool. So another example would be, let's say, limit of I don't know, x plus 9 divided by the square root. Let's do x minus 9. X minus 9 is the square root of x plus 3. As x goes to 9. That's a nice one. So, you plug in 9. Sorry, I wanted to do x minus 3? Yeah, minus 3 would give us 0. Both minuses. I wanted to create again 0 over 0 situation. There it is. So 0 over 0 situation. 9 minus 9 in the numerator is 0. Square root of 9 is 3. 3 minus 3 is 0 again. Is it undefined? No. So what should we do? Does anyone know? We can rationalize. Right? Let's rationalize. To rationalize function, we multiply by the conjugate. Right? Now, one thing that you have to get used to, otherwise you trigger my allergies, is copying the limit all the way through the problem until you get to use it in the very last step. So every step needs to have the limit. You know, when you write, 3 plus 8, well, you don't skip writing the plus. Let's say you had 3 plus 8, and then you had x minus 2, and then you go to the next step. So you go 3 plus 8x, right, and minus 16. That plus is still there. You didn't omit it next step. So keep writing this limit until you get to use it. So limit x goes to 9. I'm not going to multiply in the numerator because I have experience with these things. In the denominator, you are going to multiply, and it's difference of squares. So root x times root x is x. And then you have minus 3 root x plus 3 root x, that cancels. And then negative 3 times positive 3 is negative 9. So I hope you see what you got. This is why I didn't multiply in the numerator. I have x minus 9 in the denominator. That cancels. And your final step looks like this. See, this particular function of x plus 3 does not have a denominator, and you are allowed to plug things in. So square root of 9 is very good. Plus 3 is excellent. There is another problem where we have the answer out of, divided by 0 situation. Okay. Same problem. Limit x goes to 9. The x minus 9 over the square root of x minus 3. Trying to see if anyone has the sunglasses, but no one has sunglasses. No. That's because I do stuff that is different. All right. Anyway. So perfect. I need to borrow that now that you could have said it, but now that you put it on the table. Why are there? Anyway. So same problem. Except right now, I can't do it with it. That's right. Yeah. Anyway, so we have the same problem, and I'm supposed to rationalize, but I am not going to do that because I can factor. I go, factor what? Factor this. It's okay. I can rewrite x as root x squared. That's okay. And I can rewrite 9 as 3 squared. So I have difference of squares. So I can go limit x goes to 9, and when I factor this using difference of squares, I have root x minus 3, root x plus 3, divided by root x minus 3 that was there already. This cancels, and it's 6 right away. This is where, boss. It's the boss way to do the problem. It's just I can't do the boss way with the red glasses. I have to remember to bring my glasses for 2.3. All right, so, guys, you can factor anything. You can factor anything. It doesn't have to be x squared minus 100 for it to work. So this problem says that a squared minus b squared is a minus b, a plus b, right? And if I have x minus something that it's not factorable. I mean, that's not a perfect square, so x minus 7. All I have is root x minus root 7 times root x plus root 7. Right? And there you go, factor. Yeah, you have roots, square roots all over the place, but, you know, such is life. Deal with it. So certain problems you guys will have to rationalize. Let's see if they have some interesting examples. Then we have properties. And then squeeze theorem. And it's a wrap. Scroll all the way through to get to the homework. There we go. Nice. Finally. Okay. So this stuff is going to be extremely important. Limits with difference quotient. So in pre-calculus 1, at some point in your life, you learn the difference quotient formula. DQ stands for difference quotient, not Dairy Queen, at least in calculus course. So f of x plus h minus f of x divided by h. So that's the difference quotient that you learned. Now, you know, they just said here, learn this, and then apply it to a function and walk away. So what you are supposed to know from your pre-calculus course is how to set up the difference quotient. Now we're going to put the limit in front of it. But let's first review the difference quotient calculations. So say, so find, that's not find dq for f of x is equal to x squared plus 3. Okay. Well, you have your f of x. That's just going to plug in there as is. But you also have this piece which has function composition, and you have to actually fix that first. So let's find f of x plus h. This tells us replace every x of original function with x plus h. All right, so that's going to be x plus h squared plus 3. So I have replaced the original x over here with x plus h, which is the new variable, right? New input. Now, expand. We get x squared plus 2xh plus h squared plus 3. Generally, this term kills your grade, so pay attention. When you are squaring the binomial, you have the middle term, not just the end terms. Okay, great. So now I have all of the pieces of the puzzle. I have this piece given here, and this piece given here. So I can just plug everything in and see where algebra takes me. So what's dq? dq is going to be x squared plus 2xh plus h squared plus 3. That's the first part. Minus, in parentheses, x squared plus 3. Everything divided by h. So now, get rid of the parentheses. I shouldn't be writing this, I should be skipping the step, but minus x squared minus 3 when you get rid of the parentheses. And this is where you see that x squared and x squared cancel, and positive 3 and negative 3 cancel, leaving you with 2x age plus age squared. You can factor age and cancel the age in denominator. So dq, you factor age, you're left with 2x plus single age divided by age. This is where age cancels. And the answer is 2x plus age. So this is what we were looking for. We were looking for the difference quotient for the function x squared plus 3. And the difference quotient is 2x plus age. Now, what are we going to do in chapter 2? We're just going to put in front of each one of these limit as age goes to 0. And what are we going to do in chapter 3? We're going to call that definition for the derivative. It's a pillar of calculus. You cannot say, it's a difference quotient. It's like one of the 3 pillars of calculus, derivative. So as soon as I put the limit in front with age going to 0, which kills this age, in chapter 3, we will say that the 2x is the derivative of x squared plus 3. That's how important this stuff is. So right now we're not learning the derivative, we are learning the mechanics of working with the difference quotient with the limit embedded. So it's a 2.3 calculation, right? Where we use algebra, obviously, to massage all these terms and cancel them and so on, right? And then in chapter 3, we're just going to give it a name. And then we're going to develop on top of that. So now, we say that we want to calculate, so compute limit age goes to 0 of f of x plus age minus f of x divided by age for, and now you get, let's say f of x is equal to, let's do square root of x or 1 over x. What should we do? Anyone? Hello?
What were the choices again?
Square root of x or 1 over x?
1 over x.
1 over x. Thank you. Thank you for having pulse in the class. So what we are going to do now is set up the same stuff. We have the limit. Age goes to 0. Now, it's 1 over x plus age. Remember that x gets replaced with x plus age, minus the original function, 1 over x divided by age. And just now we need to work out the algebra of this to simplify it the most we can, and then we are going to hit it with the limit at the end. So we start with the only thing that we can do, and that is to find the common denominator and multiply everything out and technically subtract those 2 fractions in the numerator. So I need to multiply here by x, and I need to multiply by x plus age to get the common denominator. Don't forget to write the limit. Remember my allergies. So we have x. We have a common denominator of x plus age. Everything is divided by age. On top we have x minus age. So now these x's cancel. And you can put age over 1. Those of you struggling with double fractions, you multiply 2 that are far apart and put it on top, and 2 that are close by and put it on the bottom in denominator, right? So it's 1 times negative age that goes in the numerator, and you have x times age times x plus age in denominator. So that's that. Age will cancel. And what we have is the limit age goes to 0 of -1 divided by x times x plus age. What happens as age goes to 0? What do we get for the parenthesis over here as age goes to 0? X. So what's the answer? Beautiful. -1 over x squared. There it is, limit computed. Yeah, you got the function on the other end. We are going to define this as a derivative in chapter 3. But the mechanics of these calculations belongs in 2.3. So once I am talking about this in 3.1, I'll just say, remember 2.3? Right? And that's where you go and you find all of the examples. Right? This is the stuff as a question on the first exam as well. Right? I'm not going to ask you find the derivative. I'm going to say compute the limit. And then I can put the same question on exam 2 and say find the derivative. And you do the same problem. Because it is the same thing. It's just the mechanics. So now you understand that the limits will give rise to derivatives eventually in this course. So please review the formula for difference quotient. Be able to construct difference quotient from these function compositions. And then if you have the difference quotient, then once you are good with that, you can actually compute the limits which involve difference quotient in them. We have two more things to talk about. One is the limit laws, which will help us solve some really cute problems. And then we have the squeeze theorem, and that would be 2.3. So let's go with the limit laws. Number 1 is the sum. So if you have the limit of sum of two functions, f plus g, as x goes to a, you can calculate the limits individually. So limit of f plus limit of g. Right, please don't say you distributed the limit. You didn't. It's just, you can do it term-wise or function-wise. There's the same one for difference. It's just the same thing with the minus so difference. Number 3, constant multiple. So limit x approaches a of some constant c times function f. You can keep constant in front of the limit and just focus on the taking the limit of the function, and then whatever that constant was, multiply by that constant later. Product says that the limit of the product is the product of the limits. So limit x goes to a of f times g is equal to the limit x goes to a of f times limit of g. This property is not going to propagate. So the first 3 properties are going to propagate to derivatives, the 4 and 5 are not. So you have to be very careful about those. Quotient, same thing. So limit x goes to a of f divided by g is going to be limit x goes to a of f divided by the limit x goes to a of g. As long as g is different than 0, that's important, because you know, we already seen calculations that, you know, sometimes it's undefined, sometimes it's, so you have to be very careful about that. 6 power. So limit x goes to a of f raised to some power n. You can actually compute the limit of the f first and then raise everything to the nth power. So that's a cool rule. And then they have 7 fractional power. You know what? I'm just going to say with the black 7 and then just divide by 7 divide by m over here. So if you have a fractional power, that brings in the roots, right? So if you have just n, that's like a square or a cube or something. But if you have over m, then that's a square root, cube root, fourth root, and so on. So you can have any of those. And those are the rules of limits. What can we use it for? Well, let's say limit of f as x goes to 5 is defined to be 13. Limit of g as x goes to 5 is -2. Limit of function h as x goes to 5, it's important for them to go to the same number, obviously, is equal to what? Equal to 6. Okay, fine. 6.
What's the name of 7?
Fractional power. Which is you copy the same thing with n and m. Compute the limit of 3f plus 6g divided by h squared. So this is where you would use the rules as x goes to 5, obviously. So you use the rules to break this apart. First, you have the limit x goes to 5 of 3f plus 6g divided by the limit of h, and you know that you can put square on the outside because there was the rule 6. Now you can break each one of these into parts. So you have, remember, you can kick 3 out. So you have 3 limit of f plus 6 limit of g divided by limit of h squared. And now you get to swap them. Limit of f is 13. So 3 times 13 plus 6 times -2 divided by 6 squared. You swap it like a block. Limit of f, the whole limit of f. These are all x goes to 5. I didn't write it, but I should. Right, x goes to 5, x goes to 5. They're all x goes to 5. So limit of f as x goes to 5 is replaced by 13 because it was defined as in the statement of the problem. Limit of g is defined as -2, so 6 times -2. And limit of h is defined as 6, so 6 squared. And now you just need to compute this. So 3 times, that's 39, minus 12, divided by 36. So this is 27, divided by 36, cancelled by 3. We get 9 twelfths. Oh wait, cancelled by 9. What am I talking about? Cancelled by 9, so 3/4. We didn't even know what the functions were. We got the limit at the end, right? Limit is 3/4. So limit laws will allow you to do this, to do these things. And you have a few examples for that in a book. Okay, we have one more concept, and that is the concept of the squeeze theorem, also known as the sandwich theorem, depending on which book you read. I'm going to write the statement first and then explain what the stuff means. So the theorem goes like this. Again, theorem means this is the way we solve the problems. Assume the functions f, g, and h of x satisfy f of x is smaller than g of x is smaller than h of x. For all values of x near a except possibly at a. Remember that limits don't care about the point. So if limit of f of x as x goes to a is the same as the limit of h of x as x goes to a, and all of those are equal to L, some same value, right? Then limit x goes to a of g of x is L. Note that that L was squeezed between f and h, sandwiched within, right? What do I mean sandwiched? Right here. See? G is squeezed in between f and h. So now, what is the meaning of this? Well, why is it called a sandwich theorem? Is because it sandwiches the middle one. What is the function that we are trying to find the limit for? It's g, right? In this definition, this theorem, g is the unknown one that we want to compute. So now, why would we want to have this? Well, first of all, we don't have to have anything because we can compute every problem using the chart, right? That's the bottom line. But again, using chart is a little bit annoying and confusing, but then still you are going to run into a problem that is difficult to solve. So let's see if I can find an example, beautiful example. Figure out the limit of x goes to 0 of x squared of sine of 1 over x. Right? The issue is clearly here. Because 1 over 0 should be going towards infinity, actually. So what's sine of infinity? Sheesh, right? So instead, what I can do is I can use the squeeze theorem. I'm going to define function g to be x squared sine 1 over x. And then I'm going to look for f and h that will squeeze g in between. So f needs to be below, h needs to be above, and then the the function g is squeezed in between. And then if I check the limits for these guys, if their values are the same, then g has to have the same value because it's squeezed in between. Just think of the sandwich, like the real sandwich, right? You have a piece of bread, you put a piece of cheese, right? If you're allergic to cheese, put 2 slices, and then you have another piece of bread on top, right? So now, when you grab the sandwich, you are grabbing it for f and h. And wherever you move it, the g is squeezed in between, goes along with the sandwich. So we are looking for the 2 functions that are going to sandwich in g. Now, we achieve that by understanding something from pre-calc 2 because there's trig lurking around. Sine of anything over here is bounded by 1. Now, that actually looks like a butterfly. Gone. But it was cool. I'll leave it. I'll write it again. So, sine of 1 over x is going to be bounded by 1. And what that means is, yeah, come on in, it's butterflies. We have the invasion of the younglings over there. Probably they go into planetarium. So we have sine of 1 over x is bounded by 1. What this means is that sine 1 over x is in between -1 and 1. If you know your algebra, you know what this means. Now, you know that g needs to be squeezed between f and h, and when you compare the g to what you have, you see that something is missing. What's missing? X squared. Great. Multiply through by x squared and get to the line like this. Oops. X squared. Great. Now, do you see that your f is negative x squared and your h is positive x squared? Perfect. We can take the limits of those easily. So now you have the limit of negative x squared as x goes to 0, and you get 0. On the other side, you have the limit x goes to 0 of x squared, and you get 0. By the theorem, right here, written in blood. By the theorem, you have the left limit is 0, you have the right limit is 0, so the one that is squeezed in between has to be 0, right? That's the cheese part. So this one, because of these, has to be that the limit of x squared sine 1 over x is equal to 0 by squeeze theorem. We actually never worked on the limit of x squared sine 1 over x. We just used it to construct functions that are easy to work on and then compute those. So we found that the limit is. Now, if you look at the graph, it's obvious from the graph. Right? That oscillates too fast. It actually oscillates infinitely fast at 0. But the limit is 0. Remember that we don't care what's happening at the point. We care at the trend getting us to the point. So it's a very interesting problem to consider, very interesting theorem. I believe they only have 4 problems on the homework in the textbook. You probably are going to hit 1 or 2 online. try. It's hard to find these examples, so you might want to also look online, see if you can find more squeeze theorem problems to try and enjoy. And then if you have questions and problems, issues, bring them here, and we'll discuss it tomorrow more. So that's 2.3. I hope you're not disappointed. Methods and techniques. Bye.